For green hydrogen production. For the benefit of the audience, I would like to introduce our speaker. Mr. Lakhanpal is a PhD student at Technion, Israel Institute of Technology, Haifa. He specializes in computational material science, focusing on functional metal oxides and metal organic frameworks for applications in electrocatalysis and photocatalysis. Under the guidance of Professor Michael Caspary, he is developing a non-equilibrium Green's function formalization to model energy conversion materials. Previously, he contributed to the development of ceramic composites for electrolysis applications at the National Institute of Technology, Karnataka, India. His research aims to enhance the efficiency and sustainability of green conversion device. Over to you, Mr. Lakhanpal.
Thank you. Thank you very much for the nice introduction. So I will share the screen. Just a second. Okay.
Would you be presenting from your end or should we project your slides?
I'm presenting from my end.
Yeah. Okay, thank you.
So just a second. Okay. So hi, I am Lakhanpal. I am from Computational Material Science Group from Technion. First of all, I would like to thank the organizers of this conclave for inviting me for this talk. I will be talking about electronic structure to conductivity of electrocatalyst for green hydrogen production. So hydrogen has a range of applications, from petroleum refining to ammonia production to methanol production. Also, like there is a small application right now to transportation and energy production. But most of the chunk of this hydrogen goes to ammonia production right now and to petroleum refining. If we look into details, like it goes to transportation like cars, trucks, ships. So that is the future application. Like right now, it is not commercially at that scale, at that larger scale, but it has the potential. It also goes to stationary power applications, like to produce like in a fuel cell. It goes to refineries, industries like semiconductor industry, steel industry. They all require hydrogen. It has a range of applications from like power generation to space applications as well. So we have two different types of hydrogen, like we label them into two different groups, gray hydrogen and green hydrogen. There are others also, like pink and blue hydrogen, but overall, like we say gray versus green. So it depends on like from where, what is your feedstock for this hydrogen. If you are getting your hydrogen from natural gas or oil or from coal, it will be called gray hydrogen. It will be labeled as gray hydrogen. And if you are producing it from renewables like biomass or from water, it will be called green hydrogen. And we have different processes to produce hydrogen from all these feedstock. The most common one is steam methane reforming that is used in the industry to conventionally produce hydrogen at the larger scale. And in renewables, of course, like when you are producing hydrogen from the biomass, it should not come from, like you should not cut the forest and then use that biomass to produce hydrogen. That won't be called green. But of course, like in green hydrogen production, we have photocatalysis, thermolysis, and electrolysis. These three methods to produce hydrogen from the water. And out of this, electrolysis is more and more people are interested in electrolysis because of its efficiency. And also compared to other conventional hydrogen production method, the electrolysis produce very clean, like very pure, ultra pure hydrogen that can be used in fuel cells directly. And also these days we are installing more and more solar photovoltaic systems. Even in India, like we are having a lot of solar photovoltaic systems getting installed. So that so because of more and more solars, more and more renewable sources like wind turbines and all, we have grid instability. Like you will be having, sometimes you might have more and more electricity in the grid, surplus energy in the grid, and sometimes you will be deficient in the energy. Like so you have to balance that energy. Like you want that energy to be used somewhere, and that can be used for electrolysis. So this also enhances its future, because if you are installing more and more renewable sources like solar photovoltaic and wind, there will be chances that you need more electrolysis plants to utilize the surplus energy. So in electrolysis, like we have electrodes, we have membranes. So cathode and anode is there, and in between we have membrane. So those cathode and electrode, they have certain catalyst on it. That is called electrocatalyst. And we have a catalyst for hydrogen evolution reaction. We have catalyst for oxygen evolution reaction. So how to screen those materials? That catalyst is the key. If you are having very efficient electrocatalyst, you can produce more hydrogen at the same energy. So your process will be more efficient if you are having better catalyst. And how to design it? So you have experiment and you have theory. You can do, like, you can synthesize the catalyst, you can test in your lab, like you can do the voltammetry, you can measure the overpotential, you can do the impedance measurement and all those things. So that, of course, but that is a tedious tedious process. You cannot check all the parameters, you cannot synthesize all sort of materials in your lab. Here comes the theory. In theory, you can test your material theoretically. Actually, you are looking at the materials at the atomic scale. Like if you are doping your material with certain dopants, what is happening? Like, how it will change how it will improve the performance of a catalyst, what exactly it is doing. So you are looking at the materials at the atomic scale when you are talking about the theory like DFT here. So I will talk about this theory DFT, how it is used in electrocatalyst design and what it misses right now, like exactly what we are trying to address. We are using some theory like DFT and it misses few things. So I will talk about that. So this DFT, it starts from the quantum mechanics, and that starts with the Schrodinger equation. So that is S psi is equal to E psi. So you apply a Hamiltonian on the psi, wave function psi, that gives you energy eigenvalue E and returns the same wave function psi. So this Hamiltonian, it is composed of several terms and it's very mathematical, like it composed of several terms. So your real material has a nucleus that is shown here in red, and you have electron that is shown here in blue dot. So your real material is made of this nucleus and surrounded by electron cloud or electron particles, whatever you call it. And so your Hamiltonian, it composed of their interaction. So here the first two term is the kinetic energy of the nucleus and the electrons. And last three terms are the interaction between electron and nucleus. So this third term is a nucleus-nucleus interaction. Fourth term is electron-electron interaction, and fifth term is electron-nucleus attraction. So third and fourth terms are basically repulsion, and fifth term is attraction. So it is electron-nuclei interaction, and this fifth term is known as external potential of the system, and this is unique to any system. This is the fingerprint of the system. Like, just look at this term. It knows the position of each of the nucleus and each of the electron. So this potential alone defines the system, and this will be unique to the system. So from there, DFT comes from. So DFT has two theorems: Hohenberg-Kohn one theorem, Hohenberg-Kohn second theorem. So two theorems are there. First theorem says that your external potential is unique and it leads to unique ground state electron density. So there is a one-to-one mapping. For unique V external, that is of course unique to the system, will lead to unique ground state electron density. So it won't be same for two systems. It must be different, and their ground state density will also be different. There is one-to-one mapping. And second theorem says how you can find it out. How you can find it out is this ground state density. So in density functional theory, this density term is key, and you basically find out this ground state density rho naught. It says that any other density apart from this will lead to higher energy than this ground state energy. If you have energy here, E naught, then any other energy, if any other functional that will apply to this ground state, this density rho will lead to higher energy. So it's a variational principle. So there are some softwares well-written codes that find out this ground state density for you. So it is available both commercially as well as open source on the open source basis. Okay. So what we get from this ground state density? What exactly we get from this ground state density? So from this ground state density, you can pretty much define all the physical properties of the material. Actually, if you know the ground state density, you can define a lot of things, almost all the things. If you do some simplification, if you take some approximation, then of course you can define all the properties of the material. So most important thing is like density of a state, that is defined from the ground state density. So where those energy eigenvalues are located in the energy space. You have band structure. It shows that where those energy eigenvalues are in the reciprocal space. So these two informations are key, and I will explain where we need all those informations. So see how this electron density looks like. This is a small methanol molecule, and this density we got from the DFT calculation. So this is oxygen atom, this is hydrogen, this is carbon atom. And this red color cloud, this yellowish cloud around the oxygen is the electron density. Higher electron density means there are high chance that you will find electrons there. So what it tells? So this electron density itself determines the strength of the bonding, how this oxygen and carbon will be bonded. What should be their bond length? Whether it will be a single bond or double bond, it will be a covalent bond or an ionic bond. So you see here more and more charge is located on the oxygen, and carbon has less charge. Carbon has less electron density. It shows that this bond is more or less polarized. Whereas if you look at the carbon and hydrogen bond, they looks like more like covalent bond. So it's something like this we get. And if we did this for molecule, if we do this for real solids, it will determine what should be my lattice parameters, what should be my strength of the material, how much force we need to deform the material. All those things we can calculate from the DFT. And what we get from density of a state, so the same thing, same information we are getting here. In electron density, we can see that more charge is located on oxygen, and in the density of a state also we see that highest in electron states are on the oxygen, red color here. Red color is for oxygen here, and more is on oxygen. Then followed by on carbon. Hydrogen has list. Hydrogen has lost most of its electron to the carbon or the oxygen. So oxygen is in the conduction band here. If you go above the Fermi level, it is conduction band. Below Fermi level is valence band. So valence band has carbon and oxygen, and hydrogen is in the conduction band. And we get these data very easily from the DFT calculation. Otherwise, if we have to do the experiment, we have to do complicated experiments. Similarly, for the band structure, we know how those energy eigenvalues are dispersed in the reciprocal space. It talks a lot about optical properties of the material and electronic properties of the material. If these bands are flat, the material will have higher electronic conductivity. Whether it has direct or indirect band gap, that determines its optical properties. So a lot of things are there. And again, measuring experimentally, knowing the band gap, band structure of the material is very tricky. It's not easy at all. But we get this from DFT very easily. So these things we get from DFT, and this I will be showing you how we are using it in the catalyst design. So how DFT helps in studying catalysis? So it helps us to study the reaction pathway, how reaction happens. You have a product, you have a reactant, how it is getting converted to the product. It tells you about the reaction thermodynamics, it can measure the delta G. It can also measure the reaction kinetics. It can tell you the activation energy requirement for the reaction. So all those things it tells you. We can study, we are using it to study the thermal catalysis, electrochemical catalysis, photoelectrochemical catalysis. We have studied zeolite, oxyhydroxides, and metal organic frameworks using DFT. So, okay. So how we are using it to study OER catalysis. OER stands for oxygen evolution reaction. In an electrolyzer, you have hydrogen evolution reaction on one electrode, other electrode has oxygen evolution reaction. Oxygen evolution reaction is more sluggish. That's why we want to design a better catalyst for OER. That's why this is the more important question. which catalyst we should use for OER rather than HER, rather than to look for a catalyst for HER. So how we study this in DFT? In DFT, you have a surface here. Like I just showed a slab here. This is a surface, empty surface. And on the down, we have the actual material, that is nickel iron oxyhydroxide. So surface looks something like this. You have a material, you cut the surface in certain direction. You know from the literature or from crystallography which direction you should take for the reaction. Otherwise, if you don't know, then you have to check for the multiple direction. And on that surface, water will come and sit on it. It will adsorb on the surface, like this here. Water molecule came and it get adsorb onto this surface. And then at the end, you have final like oxygen. This two red color is oxygen, and they are combined together to make the oxygen molecule. This oxygen will evolve eventually. So this is the entire reaction. Of course, from water to evolve oxygen, it has several steps. It doesn't happen in one single step. It's not like that you have water and directly you get oxygen. There will be several steps in between that. And what determines this kind of reaction? It is the bonding between the reactants or the reaction intermediate with the surface. How strong or weak that bond is. Like in catalysis, you don't want that water or any other intermediate should very tightly bonded to the surface. It will be, if it is chemi-jobbed, your catalyst will be dead. So you don't want that to happen. There should be some optimum strength between the reactants and the surface. So how we study this OER thermodynamics in the DFT? So like I told you, this is the first structure where your surface is covered with the water. And this is the last structure in this cycle, OER cycle, where oxygen is evolving on the surface. In between that, you have several steps, several reaction steps, from going from water to this oxygen evolution. So, and every step involves a proton transfer or an electron transfer, something like that. So it involves that. So here you have a star H2O water adsorbed, here OH adsorbed, here oxygen, nascent oxygen that is adsorbed on the surface. So like that you have. And you measure the incremental energy for this step. Going from this structure to this structure, what is the incremental energy? What is that step energy? That determines your overpotential of the reaction. So whichever step requires
4 more minutes, please. 4 more minutes,
sure.
please.
Yeah, sure. So this incremental reaction will determine, like, how much more, like what will be the overpotential of the material. If you have higher overpotential, means that material is not good. Lower overpotential means your material is it's better. But this is from the thermodynamics. But in actual OER catalysis, it is not just the thermodynamics. In actual OER catalysis, like there is adsorption of your reactants, adsorption and desorption, that is there. And also there is an electron transfer from the surface, either from the surface to the reactant or from reactant to the surface. But in addition to that, you have electron transport from the catalyst material. This is ignored. Like you have calculated thermodynamics from the reaction, but you have ignored this electron transport. You are not accounting for that. What happened previously? This was not the issue because you were using platinum or iridium based catalyst in your electrolyzer or in your fuel cell, whatever. Those metals have very good electronic conductivity. But recently we are developing several oxide or oxyhydroxide for catalysis. They are performing good also, but their limiting factor is electronic conductivity. Oxides are generally not very good conductor of electricity. So now this question came, like, your catalytic activity, your adsorption and desorption could be very much favorable for OER, but your catalyst performance will be limited by electronic conductivity. This we have seen here, like nickel, iron, cobalt. We compare nickel, iron, cobalt with nickel, iron oxide. Nickel, iron, cobalt shows it had better performance experimentally. And this is not shown in the overpotential calculation. Overpotential shows that nickel, iron, oxyhydroxide should have same overpotential, 0.35 for nickel, iron, cobalt also. And nickel, iron, tungsten should perform worse than these two because its overpotential is higher. But this is not true. Experimentally, we have seen that these catalysts, this nickel, iron, tungsten is performing best, followed by nickel, iron, cobalt, and nickel, iron compared to nickel, iron alone. So what we did that we calculated the over potential over work function here, and we saw that work function is decreasing with the doping, this kind of doping. So this, like if your work function is decreasing, means your Fermi level is shifting up. That is a sign of N-type dopant. And in semiconductor, if you are doing N-type doping, generally it increases the electronic conductivity of the material. That's why we got the idea that we should measure the electronic conductivity of the material. And how to do that? So in our group, we have developed this formalism, NEGF formalism. We just need to do the simple band structure calculation from the DFT and do the tight binding fitting of the DFT parameter, DFT band structure parameters. From there, we are making a mathematical object called Green's function. We have self energy of the electrodes here. If we look at here, transmissions, that is your gamma L is your self energy of left electrode, gamma R is self energy of right electrode. We have GS here, that is Green's function. We make it from the band structure calculation. And our catalyst is the scattering region. Catalyst works at the scattering region. And then we are applying a voltage here, and we calculate the IV current voltage characteristic of the material. And how we do? We do it using Landauer-Buttiker formula. So this paper has been published from our group, how we are doing it. So we can measure the conductivity of the material theoretically, of any material, any catalyst. And that right now we are doing it for all those tungsten-based and cobalt-based materials in our group. So, okay, so I'll go to conclusion. So what I highlighted here is, like, you can look, if you are working on catalyst development, you can look into